All right, welcome back. We'll have another look at another example here using our model and our knowledge of integration to help. So in the word problem, it's very important that you take note of the language. So the rate of a conservation is going to be DDT something, okay, DDT usually. Now this is a number. Yes, it is a rate, but it's usually just a number. So 6 is slow, 600 is fast, etc., etc. But it's also, notice in its form, it's a differential. Okay, so it's a differential. So C prime, this thing's called prime. This means that it's being expressed in the left-hand side as a differential. Other information related to the lake is that can hold total value or total level of pollution before all the fish life ends. Can this factory pump pollution into a lake for 3 years without killing it? So we take the differential, which is dc dt. So if I put it in Leibniz notation, it's dc dt. We don't want to lose sight of that truth. Okay, and 120 t to the 12. And if we take the integral of this, we will go from 3 years and 0 years. Okay, so by f, let's do the fundamental theorem of calculus a slightly different way. Okay, we'll take the function and integrate it. But another way of doing that is to take the antiderivative at the interval endpoints, subtracting the antiderivative at the interval endpoints, remembering that the differential of the antiderivative is itself the function. This was from page 2. This was from an earlier page we did in the workshops. So what we can do, we can take the C, the concentration at time 3, minus the concentration at time 0, and integrate the differential from 0 to 3, and that will mean that we just integrate as we would normally for 120 t to the power 12 dt. Now we know that's going to be up and under, so that's going to be 120 t 13 divided by 13 between 0 and 3 by the very same fundamental theorem of calculus. Okay, and we get our scaffolding, and into the, we put 0, because it's 0 polynomial, we won't count it. For this one here, we're going to put in 3. So we get approximately a very big number. Let's have a look at 3 to the power 13. So 3 to the power 13 divide that by 13, and I've got to multiply that by 120, so you've got to be careful. You've got to be very careful. So 123 to 13 equals times 120 equals, now we can divide that by 13, and we'll get 14 million. So that's 14,716,827 is greater than 48,500. So even if I truncated this decimal, it's way above the number of fish that can be killed. Therefore, no. The answer is no, as now I'm going to write within 3 years. How much within 3 years? Okay, so that's the next part of the question, I think. If we wanted to find out how long could we wait? Okay, how long could we wait? Then we would need to work out the integral from 0 to t, and the difference would be 48.5. So we would assign the integral this value. We would assign the integral this value and solve for t. So if we integrated from 0 to t for 120 t to the 12 dt, and we assign that to 48.5, okay, we should be able to solve this integral for t given this inequation. You still have to do your integration, but it's algebraic in nature. So the output will be 120 up and under. That won't change. But this time it's between 0 and an algebra by FTC, and all of that is equal to 48,500. So that's good that we've done that. The 0 I'm not going to bother with, but the t will get the capital T. So we'll end up with 120 capital T to the 13 divided by 13 is equal to 48,500, and we're solving for t. So we're going to multiply by 13. What you do to one side, you do to the other. We're going to divide by 120. What you do to one side, you do to the other. And so t to the 13 will be equal to 48,500 times 13 divided by 120. And finally, undo. So we've got to take the 13th root of t, and what you do to one side, you do to the other. Okay, so that gives us the 13th root. So it'll be t will be equal to 48.5 times 13 divided by 120, all to the power 1 over 13. That's the 13th root, isn't it? So if we have a crack at that, we might get an indicative idea of the number of years. So we'll do 48,500. Just clear all that. 48,500 times 13 divided by 120. Okay, now we want to raise that to the power 113. So we're going to press that to the power 1 divided by 13. And we get 1.93282. So therefore, t is 1.93 years. So don't worry about 3 years. They'll all be dead within. So the company can operate for 1.93 years. Okay, so that's like a follow-up question for that. All right, 3 years they'll be all dead. 1.93 years then stop. Well, they will be all dead. It's quite straightforward, I think. All right, so the next one we want to have a look at is another example of a use of a differential that needs to be integrated. Okay, a yeast culture of 2 grams is removed from a refrigerator and expected to grow with a dWdt. dWdt, a growth rate of differential of grams per hour at a higher controlled temperature. How much will the weight of the culture increase during the first 7 hours? How much will the weight of the culture increase at the end of the 7th hour? So there's a couple of different intervals, isn't there? So we've got to integrate from the first hour our weight minus the weight at 0, which will be the integral from 0 to 7 for the differential of the weight dt, which is to say that we integrate from 0 to 7, 0.04, 0.4. We integrate 0.4 e to the 0.t2 dt. And of course what we understand is that this is able to have the 0.4 brought out the front. Now you can use shortcuts and the like, or you can stick to the program. This is a U substitution. Okay? It's a U substitution because t is being 0.2'd and then it's being e'd. Okay, so just be patient, work through it, Leibniz, stay in your column, do the work, and then we'll see that we get 1. Now, 1 over 0.2 is going to be a bit strange. du is 0. dt. So we have to do 7. You might get an argument that, don't do this, but I strongly disagree. I believe that you have to go through all of this drudgery, okay, just to become skilled at. Now, 1 over 0.2, who can tell me what 1 over 0.2 is going to be? 1 divided by 0.2, or if you like, how many times does 2/100 go into 1? And the answer is 5. So in actual fact, it's 5 du equals dt. Okay, 5 du. So u up there, yep, there we are. So we're going to put in du. We already have a 0.4, so we can times that by 5, and we can integrate, and the simple trivial one is e to the u. Now, we need to change the values. 20% of 7 will be 1.4, so we're going from 1.4 to 0. So 40% of 5, I know you'll all be doing that. 10% is 0.05, so 4 of those. 10% of 10 is 1, so it's a half, isn't it? Because it's half. So 4 lots of half is just 2. So we'll get 2. The integral of e to the u is e to the u. And so we'll have from 0 to 1.4 by ftc. And it just means that it works. Okay? So our scaffolding will be 2 e to the 1.4 minus e to the 0. Okay? So e to the 0 is 1. So our final answer is 2 e to the 1.4 minus 1. Okay? Grams. And if you put that in to your calculator, we can do the inside part of the brackets first. So e to the power 1.4. I agree, it's a bit odd. Subtract 1. That's the inside of the brackets done. Now multiply that by 2. And we get 6.11. So we'll call it 6.11 grams. Okay, so the increase is 6.11 grams. I'm not encouraging you to do shortcuts anytime because I simply don't think that they're a good idea. All right, the second part of the problem is to talk about the second interval. This second interval, we've done this one, and it's 7 to 14. So we're going to be integrating 0.4 from 7 to 14 this time. So this is very common in statistics, where you have to do multiple intervals, and you'll do that in maths too, and it uses U substitution. So that's a fair warning. Now I could miss a lot of working here, but ostensibly, is anything going to change up to this point? So up to this point, the things that will change are the limits of integration, because we're going to have 7, which will become 14, and we've got to check 14. U14 would be, I'm being a bit cheeky not laying this out, 0.2 times 14, so it's 20% of 14. 10% of 14 will be 1.4, so it's 2.8. So it's 2.8. So we're actually integrating. So if I jump a few steps, which is very, very naughty of me, and put 2e to the u between 1.4 and 2.8 by the fundamental theorem of calculus. So I've just missed all of this work here in the column, etc. And so that gives us 2 outside of e to the 2.8 minus e to the 1.4, and so that can be done with your calculator. So let's have a look at that. E to the 2.8, clear all that away. E to the power 2.8 equals minus e to the power 1.4, and multiply that by 2, so we get 24.778, so 2 decimal places will make 24.78 grams in the second interval. Wow, so there you go. So the modelling process has just been getting your wording right, getting that all to cohere and make sense, and it's a bit of work. Okay, it's a little bit of work to interpret your word problems, but well, that's the use of our practical skills in U substitutions, and learn the white paper 6 things, and putting them into a model in a real world application. All right, that's enough for applications, so we'll leave that there, and I will see you next time.